Hello, my name is Andrew, and today I'll be talking about how to count. Except this will be much more interesting counting than just like 1, 2, 3, 4, 5. I'm going to be talking about how to count infinite numbers. So let's first talk about a situation where, let's say I have 200 people, or I have 400 people at a dance, 200 boys and 200 girls, and I want to count how many people, or I want to count how many boys there are and how many girls there are, but the number isn't important so much as the number of difference there is. So I want to know if there are more boys or more girls. Well, of course I can count, and I can count on my fingers 1, 2, 3, 4, 5, all the way to 200 for each one, and then find out that, hey, they're exactly the same. But there's a much easier way to do this, which is I can simply count, I can have them all pair up, and the sad, lonely people who are left over are the leftovers. So if there's 3 girls left over, then clearly I know that there are more girls than boys. Or if there are more boys left over, then I know that there are more boys than girls. Alright, so this seems pretty obvious. But then, what happens when I have a set of numbers, like from 1 to 100 and from 1 to 10? Are there the same number of points in between those two lines, or are there a different number? Well, I can draw it out, and we can see that from 1 to 100, let's say it's something like that, and from 1 to 10 it's here. So, intuitively, we would say that from 1 to 10 and 1 to 100, obviously it seems like this set is completely contained in 1 to 100, so there should be more points in 1 to 100, right? But this actually isn't true. What if I just multiplied every single number in this set by 10? Well, what happens is I pretty much get this set. So every single number will correspond to another one without any overlapping, meaning that basically what I've demonstrated is that every single boy matches to one girl, and there are no leftovers. Fantastic. So then, but there's another case where, what if I have rational numbers which can be expressed as fractions and irrational numbers which cannot be expressed as fractions? The issue here is that both numbers are infinitely long, potentially. For example, 1/3 is 0.3 repeating, and pi is 3.14159 going on forever, right? And I can't, they're both infinitely long. How am I supposed to even count the digits in a single one? We're not even going to talk about counting how many there are yet. However, there's a very clever solution to this problem, which is the number of irrational numbers is much greater than the number of rational numbers, and I can demonstrate this by considering considering a model where I write out every single possible irrational number. So let's say that I start with let's say I start with number 0.a1.1, a1.2, a1.3, and so on into infinity. And we'll say that this is the first irrational number, where a1 represents a digit, or a1.1 represents a digit, a1.2 represents a digit, and a1.3 represents a digit. And then the next irrational number is 0.a2.1, a2.2, a2.3, and so on, and this goes on to infinity as well. And I'll continue this set all the way down to a 3.1, a 4.1, a 0.n.1, yeah? And this will go on for infinity. And this should cover every single one, because I'm literally covering every single possible combination of every single possible set of digits, right? However, there is an exception that I can find, which is if I pull out this number, a3.3, a4.4, and so on, all the way to a(n.n), and I make a number b where b1 is different from a1.1, b2 is different from a2.2, and b3 is different from a3.3. And I do that for every single digit, all the way down to bn. What happens is that I've made a number where the first digit is not the same as the first number on a1.1. The second digit is not the same as the second number on a2.2. The third digit is not the same as the third number on a3.3, and so on all the way down to a(n.n) and bn. Meaning that this number is nowhere on my list, and I have found a number that does not match to anyone. Because clearly, this matches to the set of counting numbers 1 to 100, right? It's a1, a2, a3, a4, a5, so on, so on, so on, all the way down. It's an infinite set of the same size as the set of natural numbers. However, I found an extra, which is an irrational number, and I can demonstrate this. Therefore, there are more irrational numbers than rational ones. Okay, I'm not sure.